Hello. Let's have a look at one of the examples in the Git repository. In particular, today I want to talk to you about this non-linsys example that you find in the directory non-linsys under the src directory of the examples. This is just an example to show you a use of function wrapper to define a system of functions. The idea is to use the flexibility of a function wrapper so that I can define a system of function just by inserting in the system each function at a time. So a system of function is formed by several functions, let's say 10 functions. I want to have a way of building a system of functions by inserting each function at one at a time. And we will see that this system of functions can also be used as a function factory. That is a factory that provides functions. So let's see, let's start from the traits. Traits is a technique with which we specify the types we are using in our software. We enucleate the types, the main types, inside typically a simple structure, so that we are then able to use those types in a flexible way and change the types in a more easy way. Why I want to do that? Because I may consider two possibilities, actually I'm considering three possibilities, of storing the various quantities related to the system. Let's start from the simplest one. Scalar traits. Scalar traits is the trait that I use when my system of equation is formed by equations that takes a real double and returns a double, or in any case, takes a scalar. The scalar can also be a complex number, for instance, or a float or a int, and returns a scalar. So it's a system of if you want, univariate equations. Univariate functions, sorry. So I have my argument type, that is the argument of my functions, is just a scalar. The result type of my system will be a vector of scalar, what all those functions will return. Scalar type is just scalar, and by default is double, but I may want to have a system of functions in the complex plane. Each scalar function, so each function in my system, is a function that takes an argument type that is a scalar and returns a scalar type. So it's a function of this type. While vector function type is the type of my system of equations. So if I see my system of equations as a function, it is a function that takes a scalar as an argument, but returns a vector of scalar. Function container type is the type that I will use inside my class to store the function, and is just a vector of scalar function type. This trait is repeated, but by changing, of course, the types, because maybe I want to have each function not to be a univariate function, but a multivariate function. So the argument type is not anymore a scalar, but is a vector of scalar. And maybe I want to be more sophisticated in the case of in this case, and not use a vector, but use vectors of the Eigen library, because with vector of the Eigen libraries, I can do more sophisticated stuff. So you see, by changing the trait, I change the basic type that I'm using in my nonlinear system class that I'm going to present now. So let's have a look. This is my nonlinear class. As you see, it takes a type that is the type of the scalar used. By default, it could be double. In fact, if I want, I can give a default here. I didn't do it originally, but now I can do it. But in general, it can be, for instance, complex, double, or integer. Maybe I might want that to have functions on the integer field. The second template is indeed the trait, okay, which are the default, but I can change. So by specifying the trait, I can have a nonlinear system of different type. Okay. Here I just get the types from the trait. Scalar type, scalar function type, argument type are just obtained from the trait. And the main methods are add to system, where in add to system, now if you don't remember what this construction, strange construction is, don't worry. The important thing that you understand here that add to system takes a scalar function, okay, wrapped in a function wrapper, so it can be anything, and actually takes anything that can be converted to a function wrapper, and just adds it to the system. And the system, it's here, is just a function container that is a vector of functions, of scalar functions. Then there are other methods. The most important one, in fact, are these two operators. These are two call operators. I've implemented two different kind of call operators. The first one just takes takes two arguments. The first is an integer and is the equation I want to call, and the second is the value of the argument. So this is a call operator that allows me to call a single function of the system. More interesting is this other operator, because this other operator instead considers the system as a system of functions. So it takes just the argument type, where the point where I want to compute the functions, and what it does a loop over all the functions stored in the system, call them passing the argument, and put everything in the result that is eventually returned. Okay, here just to show you a little example of OpenMP parallelism. This operation is clearly embarrassingly parallel. All those evaluations can be done in parallel, so it doesn't cost much. Add OpenMP Pragma, and if I compile with the correct option, so if I add OpenMP to my code, this will be done in parallel. If not, it will be done serially. Let's see how you can use it. You can use it in different ways. Here I'm just creating a nonlinear system that, instead of, just to show you the flexibility, instead of having function of operating on doubles, those functions operate on sign int, scalar traits, that means that a function that takes an integer and return an integer. and I just add to my system those functions. So I use a lambda expression to express the function. This is a lambda expression that takes an argument type that is an unsigned int in this case, because the argument type for for this nonlinear system is just an unsigned int in this and returns an unsigned int because in fact returns nothing else than the greater common divisor between the number I have passed as an argument and I, that is the position of the equation in my system. And here I can just, for instance, I want a greater common divisor of 333 with 11. I just call my function, the 10th function, passing 333. But in fact, I can do many other things. What I do here is just computing the result of calling NLS with 333. So if I use the call operator with just an argument, we return a vector that is the call of my functions on all of the elements of my system. And then what I can do here, I just loop over the result. And if the result is 1, it means that 333 and the position in the system are correct. Now I can have a system of 2 equations and 2 variables. So I'm using nonlinear system double, and the second trait is vector. That means that I'm using standard vector to store both the argument and the return type. So the argument type just get it from the traits, and here I'm adding, again, I'm using lambda expression just to create some function from the fly. Here is indeed a function that takes a vector of 2 components and computes sinus of the first component plus cosinus. The second is a function that I'm adding, instead computes the hyperbolic sinus and plus the hyperbolic cosinus. Then I pass a vector of 2 components to my nonlinear system. I get the result, and the result is a vector that contains the result of calling those 2 functions on this data. Okay, so eventually I have an example where I use where I show a different use of nonlinear system. So far, I've just used a nonlinear system just to create a nonlinear system, a system of equations, and call it. Okay, call it singularly, so calling the single equation or calling it as a whole, as a system indeed. But here I want to show you that the same structure can be used to create a so-called function factory. What is a function factory? A function factory is a factory that allows you to store different functions that you need in your program and recall the one that you need according to an identifier. And how does it work? Well, it just inherits from nonlinear system. So my function factory is a nonlinear system, even if the inheritance is protected, but I could have made it public. It doesn't really change much. And the only thing that we have to learn to see are the 2 important methods. The first is you add a function to the factory. When you add a function to the factory, you give the function that you want to add. Again, I'm using this trick of the universal references, or also called forwarding references. Don't worry if you don't understand them. Replace these with const fun reference, and it will work the same. Well, not the same. It may be less efficient sometimes, but I mean, from the user point, externally, it will work and will produce the same results. This is just, I'm just checking that the function that I'm passing is correctly convertible to what it should be converted, but it's not so important. What is important is that I'm adding to the system. Remember that I'm inheriting, so add to system has become a method also of my factory. I'm just adding to the system the function. And I just check if I'm not adding twice the function, because now the difference here is that I'm passing to add to factory also a string. So this function will be identified by a string. And indeed, in my factory, I have a map that maps the string to an index. And what I'm just going to do here, I inserting in the map the string and the number of equations minus 1. That is exactly the position of the function f. Because with add to the system, I've added the function to the system. So the number of equations of the system is the position of the number of equations minus 1 is the position of the last function I have inserted in the system. So now the map associates the string to the position of the function in the system. So I can get the function if I want. So I want the function identified by a certain string. What I do, I just check if this string is in the map, and if it is in the map, I just return the function using the method getFunction of my nonlinsys. It just returns a reference to the function of the position given in the argument. If it is not, if the string does not correspond to any function, well, I throw an exception. I say, sorry, this function is not present in my factory. So now I go back to the main. Here I'm using my nonlinear system as a factory. Here's a factory that scalar traits, so it means is a univariate functions, is a set of univariate functions. I add function 1. This is function 1. It's just the sinus. Function 2 is just the cosinus. And then in my code, I need function 2, and I will just call factory get function 2. So this factory can be used in your code in the case you have the need of storing many different functions, maybe, I don't know, different random number distributions, different I don't know, different type of different boundary conditions, whatever, and you want in your program to be able to recall one or the other function just by passing a string that identifies the function. Okay, enjoy this code. You can run it. It works, and let's move to the next example with the next video.